The world is constantly changing, driving continuous innovation from the cloud to the edge. Data growth is relentless, and ever-changing market dynamics are making it harder to get your products launched ahead of the competition. You need Xilinx. Today's applications demand a new approach to computing, one that seamlessly adapts to your constantly changing environment and handles complexity with ease. That's our adaptive platform, and it's redefining the way the world thinks about accelerated workloads. Xilinx delivers the powerful tools you need to build the adaptable, intelligent world today, and the flexibility to adapt to whatever the future may bring. Don't just imagine the future, create it with Xilinx, because a better world can't wait. Xilinx, building the adaptable, intelligent world.
Hello, everyone. Welcome to my presentation on AutoML and once-for-all network on FPGAs. My name is Song Han, a assistant professor of MIT. So today's AI is too expensive, and we need efficient and green AI. For example, training a single AI model can emit as much carbon as 5 cars in their lifetimes. So here is the common carbon footprint benchmarks. A US car, including fuel, is about 126,000 pounds of CO2 emission. But a transformer with neural architecture search, called evolved transformer, will emit as much as 600,000 pounds of CO2 emission. So we need to design those efficient models that's consuming less computation for both inference and training. And this used to be a black magic, where people have to manually design the neural network architecture to achieve a target latency and target accuracy. For example, people have to manually tune the number of channels, number of branches, the resolution of the input, the kernel size, and the layers, and even more. Such manual design method used to be very notoriously hard to tune. Therefore, we are working on AutoML techniques and neural architecture search approaches to automatically design and synthesize those efficient neural nets to fit a target latency, accuracy, and memory constraints. So we use a lot of computation, use AI to automatically design those better AI models, given the latency and energy feedback. So such AutoML method to a neural network is like an EDA tool to circuit design. Given a large design space, we can automatically figure out the best match neural network architecture. So such AutoML approach is very effective on Xilinx FPGAs. For example, measured on Ultra 96, the Z03 FPGA, our AutoML method called proxyless NAS can design the efficient and specialized neural network models for the FPGA without changing the RTL. So such a pure software solution can improve the utilization of FPGAs. And it is compatible and complementary with the Xilinx Vitis AI toolchain. For example, with the same image net accuracy, without AutoML, the latency is about 6.2 milliseconds. But with the help of the AutoML technique, it runs only 4.2 milliseconds. On another platform, slightly larger FPGA, the ZC102 with the Z09 FPGA, without AutoML, the latency is 2.8 milliseconds. But with AutoML, proxyless NAS can accelerate it to 1.9 milliseconds only. Okay, so such proxyless NAS method is very effective to deal with a single FPGA platform. What about we have multiple FPGA platforms? For example, a U280 for the cloud and also a Z03 for the edge. Apparently, the U280 has much more resources than the ZU3. But designing those neural networks of different sizes to fit different size of computation budget will be very computationally expensive. Therefore, can we design just a single model, and then we can select different subnetworks to fit different computation resources. For example, we can select a larger subnetwork to fit a cloud GPU and the cloud FPGA, and we can select a smaller subnetwork to fit an edge device. And this method need to be trained only once and get many subnetworks that can be deployed without any retraining. And this way can reduce the design cost. And also it can fit diverse hardware constraints without incurring a lot of extra computation. So during training time, we randomly sample different subnetworks during training time so that smaller networks can be trained without losing the accuracy. But naively sampling the model will suffer from accuracy loss. Therefore, we also proposed this progressive shrinking technique to start with a larger model and then gradually sample smaller and smaller subnetworks. So compared with a conventional approach, the conventional neural architecture search approach, which has 2 for loops. One is a microcontroller, the other is for different devices, which is outside this very expensive forward and backward loop. That's why it's very expensive due to these actual for loops outside this forward and backward loop. So once for all model decouples training and search. So it need to be trained only once for this super network. And then we can perform architecture search on this pre-trained model. And we just need to sample the subnetwork from this once for all model. So for different devices, for different search episode, we just need to sample a subnetwork from this once for all model. And this doesn't require any retraining. Therefore, the sample time is very fast. This is very lightweighted. So this is the effectiveness of weight sharing and decoupling training and search. So as a result, the search cost measured with the amount of CO2 emission can be reduced by 4 orders of magnitude compared with the conventional microcontroller-based neural architecture search approach. So surprisingly, we can train 10 to the 19th different subnetworks at the same time. We can train once for all model and get many child nets for free without any retraining. This borrows the idea of human brain, where human brain activates sparsely. Not all the neurons are activated at the same time. So this once for all network contains many child networks that are sparsely activated. Those child networks share the weights with the once for all model, and they are trained jointly. Since they share the weight, the total storage required by different models is very small. Such OFA model is very effective on Xilinx FPGAs. We can achieve higher arithmetic intensity on FPGA using the once for all model, which is in green, compared with MobileNet V2 and MNASNet. So arithmetic intensity is defined as operations per byte. When you fetch 1 byte of data from memory, how much computation can you do on top of it? Since computation is cheap, memory reference is expensive. Ideally, we hope to have more operations per byte. So OFA model improved the arithmetic intensity from about 37 to about 50. So this is just by smartly designing the neural network model without changing the RTL. And that effectively improved the GOPS per second, the throughput measured on Xilinx FPGAs. Again, just by smartly designing the neural network model without needing to change the RTL. For example, on ZU9 FPGA to the left, we improved the throughput from roughly 100 GOPS per second to 155 GOPS per second, while giving even better accuracy compared with MobileNet V2 and MNASnet. On the right-hand side, on the ZU3 FPGA platform, we improved the throughput from 44 or 48 GOPS per second to 76 GOPS per second, more than 50% improvement of the throughput. So we not only designed the efficient backbones, but also designed the end-to-end application. For example, video recognition is a very important application, both on the cloud and also on the edge, since the amount of videos are growing exponentially. On the bottom left, we are showing a demo for video recognition. For example, we can classify moving something closer to something, hitting something with something. And this used to be very computationally expensive because it requires not only spatial modeling, but also temporal modeling. Conventional methods used to require 3D convolution, which is very computationally expensive. We proposed a new approach called the temporal shift module that uses a simple shift method plus 2D convolution, but it can achieve even better accuracy compared with the 3D convolution. So on the top right corner, we effectively reduced the computation by 6 times, but we improved the accuracy by a large margin. On the bottom right corner is showing the effectiveness of large-scale distributed training. Since TSM is very parameter efficient, there are fewer gradients that need to be communicated during distributed training. Therefore, it is very scalable. So from one node, the training time is more than 49 hours to 256 nodes, where we reduce the training time to only 14 minutes. The speed up is 211 times, which is almost linear. So we deployed such video recognition algorithm TSM on the FPGA. For example, in this demo, we can classify swiping left, swiping right, different gestures, or swiping up, swiping down. We can also classify, we can zoom in the map and zoom out the map by purely using gestures. Other activities such as drumming the fingers or a stop sign can be clearly recognized. And altogether, this system is taking only 10.3 watts. Here is a comparison about the speed, the inference speed of the video recognition algorithm on different hardware platforms. And all these platforms are edge devices, ranging from a Raspberry Pi, it runs 14 frames per second, and Google Pixel 1, and Galaxy Note 8 is about 21 to 29 frames per second. We also implement that on mobile GPUs, including Jetson Nano and Jetson TX2. After auto-tuning and quantization, we can run it about 70, after auto-tuning without quantization, we can run it at 75 frames per second to 118 frames per second. But on the FPGA with the ZU104 device, we can run it at 160 frames per second. All right, that's all for my part. With that, I would like to switch and to hand it to Nick Ni, Director of AI Products from Xilinx, to talk about how you can target FPGAs with no hardware experience. It's your turn, Nick.
Thank you so much, Dr. Han. It's my pleasure to resume this talk. My name is Nick Ni. I'm a Director of Product Marketing for AI software and ecosystem with Xilinx. Now, following up to Dr. Han's talk, I'd like to introduce you to what you can get started with the Xilinx tools. Now, this is a very important topic because traditionally, Xilinx FPGAs has been known for hardware developers, but we've been investing heavily in enabling and expanding the user base into people like you, AI developers. So let me introduce you to Vitis AI, our AI software stack for inference. The idea is very simple. You can directly take your trained neural network from PyTorch, TensorFlow, or even Caffe and feed into our tool and directly run on FPGA devices. So we provide you with AI model zoos, just like how you are using with the TensorFlow zoo. And we provide you with a suite of tools such as AI Optimizer, AI Quantizer, AI Compiler, and Profiler. And this will take care of compiling your TensorFlow or PyTorch graph into an executable for FPGAs. And then we provide you with a runtime and also pre-optimized IP, so you don't have to develop hardware IPs yourself to run CNN or RNN or BERT. And this whole process can be done in minutes, just like how you would do on the CPU and GPUs. And let me give you an example of a typical vision-based use case, such as video analytics. In many applications, before you start doing neural network, you receive streams or multiple streams of video. And those are often coming from cameras, which is encoded in H.264 or HEVC. So the first step is to decode these frames using, say, a decoder, and then you apply some computer vision processing to resize it, scale it, or crop it the way you like for your neural network. And then there's typically a first stage where you do some kind of detection, see what are the interesting objects you want to do some follow-up on. And then based on the number of interesting objects, you may apply different kind of classifications. Maybe you are trying to detect what's the item in the retail store. Maybe you're trying to detect if that person's gender, or maybe it's a license plate of the car. So in these kind of processing, not only requires you to have multiple neural network running in the same frame, could be more than 10 neural networks, but also you have pre-processing like video decode and computer vision. And often there's a post-processing with the encode and some kind of object tracking. Now to enable this, we've also introduced an SDK called the Vitis Video Analytics. And this allows you to go even higher level of abstraction using industry standard framework such as GStreamer. Now you can do everything using open source framework and absolutely no hardware development experience necessary. And the results was quite impressive. We have two key platforms, one for the embedded system on module type of form factor called Korea Song. And this outperformed the state-of-art system on module such as NVIDIA Jetson TX2 by almost 2x. Now on the PCIe form factor, our latest 7nm Versal has a board called VCK5000. And this one has outperformed the state-of-art GPU such as NVIDIA T4 by almost 2x in the entire pipeline of video analytics. So again, thank you so much for your time. I'd love to give a special thanks to Dr. Han for his talk. And if you are interested in the next steps, you can go to xilinx.com/AI to find out all about the software stack and the value proposition using AI on FPGAs. And for those cards, PCIe cards and the embedded Korea Song, you can also find a link to get access to those. Thank you so much for your time.
Intelligent video analytics touch all aspects of daily life. With smart algorithms, digital video feeds can be examined pixel by pixel for many applications. And now with the new Vitis Video Analytics SDK from Xilinx, this analysis can be done much faster than ever before. That's because with Xilinx, you can process twice as many video streams as marketing-leading GPUs in the same amount of time. It's a complete software stack for edge-to-cloud video analytics on Xilinx platforms. The Vitis Video SDK includes video decoding, pre-processing, AI inference, tracking, and post-processing, all in one package. And it supports widely used AI models for real-time object detection, classification, and segmentation. Use it to study traffic patterns in smart cities. Support self-checkout in retail stores. Or detect component defects at manufacturing sites. Or come up with an application of your own. The possibilities are endless. Get started today and deploy in just weeks. What are you waiting for? Visit Xilinx.com to learn more.